So up to this point, we've looked at the ideal gas law and how it applies to static conditions. In other words, when nothing is changing. But what about when something is changing, when pressure changes or volume changes or temperature or moles change? How can we use the ideal gas law then? And so we're going to look at the ideal gas law in a little bit different way. And let's start off with just the plain ideal gas law. PV equals nRT. Now remember, R is a constant, so what I'm going to do is I'm going to isolate it. I'm going to divide both sides by N and T. And when you do that, the N's cancel, the T's cancel, and we're left with R on the right-hand side. So I get P times V over N times T equals a constant, R, the universal gas constant. And so if I have a balloon, and it's sitting there, and it's got its gas particles inside of it, and I measure the pressure, the temperature, the volume, and how many moles there are, and I plug those values into this equation, I will get the value of the universal gas constant. That's the way I can derive the universal gas constant. So if I take these conditions and I change it, like let's say that I shrink the balloon, and inside that balloon the particles are now crammed together, the same number of particles. I didn't change how many particles there were, now they're crammed together. So the pressure is going to change, and let's say I heat it up, so the temperature changes. And let's say I put a few more particles in, so the moles change. Everything changed. Well, it doesn't matter. The pressure of that new balloon times the volume of that new balloon divided by the moles of that new balloon divided by the temperature of that new balloon still is going to give me the exact same constant. That's what makes it a constant. And so what I have here is a situation where I have an initial balloon, P1, V1, N1, and T1. That's our first balloon. And I have a second balloon, P2, V2, N2, and T2, and it doesn't matter what the conditions are, they're always going to have this relationship equal the universal gas constant. And so what that means is if both of these equations equal the universal gas constant, then I have a really handy way of writing this, because now this equation and this equation equal each other. And I get this P1 V1 over N1 T1 equals P2 V2 over N2 T2. I get a very useful form of the ideal gas equation where I can solve for changing conditions. And so now, if the pressure changes, the volume changes, the moles change, and the temperature changes, I can solve for the new conditions if I measure some of those new conditions. And so a practical example will help out with this, and we'll learn how we can use this to substitute for all the other gas laws that we've used up to this point. And that will be the topic in our next example problem.